Well, hello there. Hello again. Hey, I feel a little bit like an internet sensation today. My little shiny video from yesterday, last I looked, it's got over 200 views. Now, to me, that's like going viral, but in a good way. So, all right, where are we at? Let me do a little screen share here. So it is Friday, April 17th, 2020. Sorry, I'm being distracted by the deer walking through my yard right now. One of the advantages, I guess, of working from home. Friday, April 17th. What are we talking about today? Well, we're going to get into that metallic bonding just a little bit more. This will be a fairly short one. So what do I want you to be able to do? I can define metallic bonding, including a description of what happens to electrons. I can name some properties of metals and explain those properties in terms of what's happening with the electrons. Are you catching on a theme here? We're talking about electrons. I can define alloy and give some examples of some common alloys. So let's just get into it. Metallic bonding. This was just a link to that shiny video from 2 days ago. You know, the one with the big crab. All right. So we're talking about metals here. And if you think about what you know about your valence electrons, metals, all the atoms have just a couple of valence electrons, one or two, sometimes three, and none of the atoms have a very strong attraction for their electrons. You know, you think about how different that is from ionic bonding. In ionic bonding, you had two atoms, one of which had a very strong attraction for electrons and one of which didn't. And so the one with the stronger attraction takes an electron away from the other. That's creating your two oppositely charged ions. But here, it's like we've got everybody has the electrons to give, but nobody really wants them. So what's going to happen? Well, the result is that the valence electrons are not tightly bound to any one atom, but they're also not just locked up between two atoms. Instead, what happens is our electrons are able to move around. It's basically shared among all of the atoms. So let me try to explain this diagram a little bit. So I've got the pluses in the background are representing our atoms. It's representing the nucleus of the atoms and all the inner electrons. So the nucleus is positive, so it is positive. And let's just imagine that each of these atoms has one valence electron. So overall, this network is neutral. You've got atoms, they each have a valence electron, but they're all neutral atoms. But instead of this electron, each electron being locked up with one atom, just imagine that an electron can drift to another atom. And in this particular example, I have all the electrons kind of linked together. So the electrons are able to just kind of move around. And that's going to be really significant. Now, we often see in textbooks and things it described as a mobile sea of electrons. You got to think about what that means. Now, I've been in the ocean, and I can just sort of visualize where you're in the water and there's a school of fish, and there's surge in the water where the waves are moving back and forth, and you'll see this entire school of fish all together just drift over this way, and then they drift over this way, and they drift back, and they drift forth. That's how I kind of envision these electrons in an atom. And it's going to relate now to the properties of metals that we talk about, this mobile sea of electrons. Now, I'm going to have you watch another little video that I took in class a couple years ago, where in this one, you've got a whole, the seats full of students, and each student has a little tape roll, and that's representing their electron. And so imagine that electron drifts over to one of their neighbors. And so it might end up, because I'm not real attracted to my electron drifts over to a neighboring atom, and their electron drifts over to another neighbor of theirs and their electron. And so what you see in this video is these electrons are just kind of moving around through this cluster, through this network of ions. I sometimes also try to describe this as the communist bond. And by that, what I'm saying is, it's not your electron, it's not my electron, they're all our electrons. We share all the electrons communally. All right, so let's get into some of the properties of metals. Metals are good conductors of heat and electricity. Well, I'm going to pop back to that previous page. And what happens, let's imagine that somebody brings, how about a big negative charge over to this side of our piece of metal? Well, what's that going to do? Well, all these electrons are negatively charged, and they don't like these negatives. So if there's an excess of negative somewhere, well, the electrons are all going to move away from it. Hey, if you've got moving electrons, you've got electricity. This is a good conductor because the electrons, the little charged particles, are very free to move around. What else we got? They're shiny. Metals are shiny. Yeah. They have this metallic luster. Well, let's go back to our picture. It turns out, because these electrons are not so locked up into those different energy levels, I mean, they got to have a place to go, but they're drifting between atoms, and they're getting into all different energies, and apparently they're able to absorb a really wide range of energies and then re-emit those energies. And that's where we get that shininess from metals. Is light falls on it, jiggles the electrons a little bit, the electrons re-emit it. And in many cases, it's re-emitted in much the same way, the same wavelength, the same type of light that fell on it. And so we get that nice reflectance. So yeah, we can use a mirror. We can take a piece of glass and put a metal on the back of it. Traditionally, it was silver. You put silver on the back of the piece of glass, and now the light from your face, actually light bouncing off your face, hits the mirror and bounces back to your eyes, and you see that reflection of your pretty face or whatever you're working with. What else do we have? Malleable. Okay. I'm going to go to this picture. Remember, with my ionic compounds, I showed a crystal lattice, and we hit it with a hammer. And when we hit it with a hammer, we knocked things out of place, and we created repulsions. But in a metallic bond, if I take this hammer and bring it down and hit this, and I move a couple of these positives, okay? Now, these positives don't like that. They're getting closer together to other positives. But if in this metal, I create an excess of positive charge somewhere, well, now what's going to happen is electrons are going to move towards that to balance it out. And so the fact that the electrons aren't locked up anywhere, that they're so easy to move, they can counter these repulsions before the repulsions just make things fly apart. So metals, when you hit them with a hammer, are much more likely to dent or bend or reshape, unlike non-metals and ionic compounds, which, you hit them with a hammer and they just shatter into a billion pieces. It all comes down to the mobile electrons. Okay, I think we got one more here. Metals generally have high melting points. Now, there's a couple of exceptions to the rule, and I mean, some metals have relatively low melting points. Mercury is a liquid at room temperature. Gallium will melt in your hand. But most metals have relatively high melting points. And what that tells us is that while this bond is rather flexible, it's not weak. what is actually holding this all together? Well, if each atom effectively loses an electron, that makes it a positive ion. And then you've got negative electrons drifting around. And there is an attraction between positive and negative. So every positive ion in this network is attracted to every negative electron in this network and vice versa. And it's all being held together. And it's being held together strong enough that it takes a lot of energy actually to separate these somewhat and turn them into a liquid, and certainly a lot more energy to turn them into a gas. The stronger the attraction between the particles, the higher the melting point. So apparently there's a few metals that aren't as strongly attracted. So, mercury and gallium, etc. But in general, these are pretty strong bonds. Even though it's a flexible bond, doesn't mean it's not strong. So, last thing we have here is an alloy. So, effectively, an alloy is when you have a mixture of two or more elements, and at least one of them is a metal. Generally, I think of alloys as being mixtures of metals, but it can be where you have a metal and you've added a non-metal to it. So it doesn't have to be all metals, but at least one metal, and it's a mixture. The alloys are really significant to us because, on the periodic table, we've got about 90 naturally occurring elements. And those are the things that we can use to do everything that we do on this planet. And there's quite a few metals in there. The thing is, each of those metals has its own specific properties, but those properties may not perfectly line up with the use that we want to put them to. And it turns out by mixing elements together, by making these alloys, we can create an alloy that's got superior properties to any of the individual elements. In reality, I think it's pretty rare for us to use a pure element. Okay. Bilbo's ring in the background here. Yeah, it's supposed to be gold, and for movie purposes, they probably want you to think it's pure gold, but it probably isn't pure gold because you know what? If you take a ring and you make it out of pure gold, while gold is very chemically resistant and it's shiny and doesn't corrode, but if I knock my ring accidentally on the table or on purpose on the table, if it's pure gold, it turns out it dents and bends really easily. Gold is one of the most malleable elements on the planet. I think it is the most malleable. Don't quote me on that. So, sorry, I'm stumbling on my words here a little bit. We rarely make jewelry out of just pure gold because it doesn't keep its shape very nice. So what do? You add some other elements to it. So this is, I believe, 14 karat gold. I'm not certain of that. If you start getting down to 10 karat gold and less than that, that's where, if you've got some skin sensitivities and things like that, sometimes that jewelry, will discolor your skin and possibly some allergic problems, some allergy problems. We mix elements together. A really useful element out there is iron, but most of the time the iron is mixed with some carbon and often lots of little bits of other elements to make various types of steel. Oh, steel is really useful. See, iron by itself is a little bit on the brittle end of metals. You hit iron, a piece of cast iron with a hammer, rather than denting, it may very possibly break. But if you add a little carbon to it, you just made it into an alloy called steel, which is much more malleable and workable. So I have some examples here of some common alloys that you've probably experienced. You've been around. So certainly steel. Steel is iron with carbon, a little bit of carbon. And then we often add little bits of other elements to the steel to kind of fine tune the properties. So an example, stainless steel has chromium in it, or possibly some vanadium in it, some nickel in it. And, they add enough, if you put enough chromium in the steel, now you've got steel that doesn't rust. All commercial kitchens have to be made of stainless steel products. Oh, okay. Bronze was an alloy discovered in ancient times, and it's an alloy of copper and tin. Copper by itself is too soft. It's one of the early elements that humans discovered, but it's too soft to make really strong tools. If you try to make a copper axe, you start chopping your tree, your axe is going to get dull in a hurry. But if they add a little tin to the mix and cast a bronze axe, that's a much stronger tool. Brass is an alloy of copper and zinc. We see brass fittings on a lot of plumbing fixtures, gas fixtures, things like that. And then I have the example of 14 karat gold here, which is actually the mix for 14 karat gold is 58.5% gold, 29% copper, and 12.5% silver. Okay, those are some alloys that you are probably familiar with. So if you're talking about metallic bonding, oh boy, you better know what's happening with electrons, because those electrons are what create the properties, those very special properties of metals. So I'm going to stop this screen share here for a little bit. So yeah, we got a couple of metals here. You can possibly see, right up here, there's Bilbo's ring, right over, I wait for my hand to appear here. There's, his sword Sting. Don't know if we can tell if he's wearing his mithril shirt that he gets. No, that's probably later on in the story. But hey, some cool metals there. Thanks for watching. I hope you're staying safe. As always, if you have questions, let me know. I'm available. I'm here for you. And let's keep some education moving along. So have a great weekend. Bye-bye.